What exactly are the W and Z bosons? Are they just short-lived particles? Or are they, in fact, fleeting entities born during a transition process where identities are redefined? According to textbooks, weak interactions are mediated by W and Z bosons. And when quarks within neutrons emit or absorb W bosons, they undergo a flavor change, transforming a neutron into a proton. This is typically accompanied by Feynman diagrams and formulas for half-life. However, there are two significant points that the textbook explanation leaves out. First, what exactly happens when the W boson is emitted? The books only describe a complex reorganization process, reducing it to simple lines intersecting and giving the intermediate state a new name. Second, while the W and Z bosons might appear similar to particles like the electrons in diagrams, they only exist for a brief moment in the real world. Textbooks rarely explain their identity in the physical picture, instead only letting us remember them as two short-lived, heavy particles. In the energy filament theory, we choose to think of this differently, using the concept of circulations instead of particles. A neutron isn't a solid sphere, it is a combination of three quark loops that are bounded together. Each quark itself consists of an extremely small loop of energy filament and a directional straight texture. These three quarks are connected by colored texture bridges, forming a closed triangle that is stable enough to exist as a neutron. When weak interaction occurs, what really happens is a reorganization of these quark circulations. As the structure shifts from neutron configuration to proton plus electron plus antineutrino, the quarks' circulation paths are rearranged, the original flow lines are undone, rerouted, and reconnected. This is not a seamless, instantaneous process. There will inevitably be a temporary pressure in certain regions, causing a localized area of tightly wounded, high-tension circulation, akin to a large whirlpool. This is what the equations refer to as the W or Z boson. It is a concentrated circulation, but not yet identified as electron circulation or neutrino circulation. Instead, it is a transitional circulation package, created to temporarily handle the excess tension during the reorganization process. This state is unnatural, and the energy C does not allow it to persist for long. The next step in this process is the filamentation stage. The circulation quickly leaves marks on the surrounding boundaries of the energy C, carving clear small filament rings in what was previously a relatively smooth texture. These filaments are reorganized into various subparticles. Some turn into electrons, others into antineutrinos, and still others form new quark loops. The strong force then takes over, grouping quarks into mesons and hadrons. Once these specific loops are created, the original W or Z transitional circulation is dismantled into several independently existing particle loops, and its role as an intermediate state dies. At a glance, we might say that the tension difference is carried away by the electron and the antineutrino. However, a more detailed picture reveals that the transition boson W or Z initially becomes a high-tension circulation loop that is subsequently filamented in a short time, breaking down into these endpoint particles. Compared to gluons, which are circulation wave packets on color bridges, primarily focused on patching up gaps, W or Z bosons focus more on reorganization. After reconfiguring the structure, the resulting high-tension circulation is divided into two main categories, leptons and quarks. This is the fundamental difference between W or Z bosons and gluons in the energy C. By understanding this process through the energy filament theory, we gain a deeper insight into how the weak force operates not through an added force, but via an internal reorganization of particle structures driven by the filamentation and redistribution of tension. In essence, the weak force helps reconfigure particles' internal texture, leading to their transformation and eventual decay. In the following episodes, we'll dive deeper into the question, what determines how long unstable particles live? Stay tuned, tap follow, and share this content on. We're bringing new physics to light and helping you see the universe in a whole new way.